We're going to start this unit by stepping back to Unit 2 and revisiting a special case rule that allowed us to take the derivative of a function when there was another function inside of it. This special case is actually called the chain rule, and it's used to differentiate what we call composite functions. I always like to think about composite functions as the cakes of calculus. So imagine you're baking a cake. You start with the raw ingredients, you mix them together, then you bake them in the oven to get the final cake. The process happens in steps. One function, the mixing, feeds into another, the baking, and then the eating. In math, some functions work the same way. An inner function is processed by an outer function to produce a final result. These are called composite functions, and we use the chain rule to differentiate them. We're going to add the chain rule to our rules to live by today. Let's take a look at what rules we have so far. So, on our rules to live by, we have the power rule. That I think was the very first one that we learned, where if we have x raised to the power of n, the derivative of that, we bring the power down, and then subtract 1 from our power. If we have a constant attached to either a power or just by itself, the derivative of that will be 0. Then we looked at what if we have two functions that we're adding or subtracting. We had the sum and difference rule. Well, that one was simple. We take the derivative of the first one and we add or subtract the derivative of the second one. Right there. Then we had the product rule if we're multiplying two functions together. Now, this is where we start having a few more moving pieces. So if I have f at x times g at x, my derivative will be the derivative of the second times the first plus the derivative of the first times the second. I think we did talk about that slightly differently, where we said the derivative of the first times the second plus the derivative of the second times the first. But because we're adding them together, the order doesn't really matter. Then we'd spent some time just in this last unit looking at the quotient rule, where I have one function divided by another. Now, this is where order does matter because we are subtracting on the top. So we have derivative of the first times the bottom, or top times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. And this is where I gave you that little mnemonic, I guess. It's not really a mnemonic. It's just a little sing-song where you have low d high minus high d low all over low low. We need one more rule to cover these composite functions, and as I've said, that's the chain rule, and that's what we're going to take a look at today, and we're going to start off by looking at what actually makes something a composite function. Many functions are combinations of simpler functions. So let's start just by looking at an example and putting some language around what we're talking about. So let's say I have two functions. I have f at x is equal to x cubed, and I have a g at x that's equal to 2x. Then if I wanted to put them together, I could say a separate function h at x could be equal to x cubed plus 2x, which could just be expressed how we're used to seeing it, is that the function would be equal to f at x plus g at x. Composition or combining functions, when we're doing that, we're starting with a number x that's in the domain of g. Then we're finding this, what we call the image of g at x. So we take the value of g at x that's in the domain of f and create a completely new function. Now, if that sounds like, what the heck are you talking about? As soon as I show you what I mean, you'll understand. So our new function, h at x, will be some combination of the two. So in this case, let's say we have f and we have g at x in the middle. Now, think back to other math courses that you've taken. If I showed you that, typically you would know that you have one function inside of the other. If I know both functions and I have some value of x, really what I'm being asked to solve for here is, what will my function f at x equal if the value that I'm solving f at x for is actually g at x for some value? When we're talking about this as a composite function, we can actually denote it a little bit differently than that. So it can be denoted using f with a little circle g, and that just means that little circle means composed with g. So f is composed with g, or we could say f of g of x. So we're taking the value of the function f when it's combined with g, and g will have a solution of when the value is x. Let's take a look at some composite functions. So we have two functions here. F at x is equal to x squared plus 1, and g at x is equal to 2x minus 1. So here's our question. Does f of g at x equal g at f of x? So let's break it down and see which of the following situations might be true. So let's start by looking at f of x plus g of x. And we want to know, well, does that equal, if I reverse it around, g of x plus f at x? And if we think back to our product rule, I think we know that yes, it probably is going to, but let's do the math anyway. So f at x is x squared plus 1, g at x is 2x minus 1, so we're just going to add that, 2x minus 1. And will that equal g at x, which is 2x minus 1, plus f at x, which is x squared plus 1. So we're going to collect like terms on each side. So I end up with an x squared plus 2x. The 1's cancel out. And on the other side, I'm also left with an x squared plus 2x. So yes, that does equal. So yes, it does. Now let's take a look if we're multiplying or we're taking the product. So if I have f of x times g of x, will that equal g of x times f at x? Well, let's take a look. So I have x squared plus 1 times 2x minus 1, and will that equal 2x minus 1 times x squared plus 1? We're going to expand that out and simplify. We end up with 2x cubed minus x squared plus 2x minus 1. And on the other side, we also end up with 2x cubed plus 2x minus x squared minus 1. Oh, I've got that in a little different order, but I think we can see that, yes, they do equal each other. Now, what if I have... So these are what... Sorry, I'm going to step back. So these are what we call combinations. Combinations. So we have combinations of addition, subtraction, multiplication, or division. So we can see that if we have some combination of those four operations, then yes, they will be equal to each other. But now, what if I have the function inside the function? And I just need to add an extra page here so that we can go ahead and do that. And I'm going to put the square paper. So now we still have our two functions. We have f at x is equal to x squared plus 1. And we have g at x, or g of x, is equal to 2x minus 1. So now, will f at g of x equal g at f of x? That's what we want to find out now. So we're going to put this together. So we have x, and x will be, in this case, 2x minus 1. That's our g of x. We are now going to, now we have f, which is x squared plus 1. We're going to put this, all of g of x, into where there is an x squared. And that will result in our f at g of x. So that leaves us with 2x minus 1 squared plus 1. Now let's look at it the other way around. So that's f at g of x. Now let's look at g at f of x. So we are starting with x, and our x value in this case will be our f at x, which is x squared plus 1. Our g is 2x minus 1, and we are going to put this into where the x is in our function g. That gives us a g at f of x equal to 2 times x squared plus 1 minus 1. So we can see from this that f at g of x does not equal g at f of x. So this is what we call composition or substitution. So what we've done here is actually combine the two functions together. So it's a combo of functions where one function gets substituted in the other to create a new function. The only purpose of this whole thing in these last two slides was really just to show you how we're putting the functions together. It's one function inside another. Sometimes if we combine them using addition, subtraction, multiplication, or division, they will be equal to each other, but when we put one inside the other as a composite function, they will not be equal to each other if we flip them around. So now let's get this rule, this chain rule, hammered down for derivatives and composite functions. So by the end of this lesson, really the goal of this is to get you more comfortable with using the chain rule in Leibniz notation, which I know I don't normally use, but we're going to use it in this lesson, to determine the derivative of composite functions. So the chain rule, and this is what you're going to add to your rules to live by. So the chain rule states that if I have one function that's equal to another function put inside that function, so now I've got another function that's inside a function, then if I want to take the derivative of this, remember back to what we did, the derivative of that whole function will be equal to the derivative of the outside times the inside times the derivative of the inside. So derivative of the outside times the inside times the derivative of the outside. So let's look at an example. So we have a function here, h at x is equal to the square root of 2x squared plus 3. We're not going to panic that this is a square root because remember, I can rewrite the square root as a power. So if I rewrite this as a power, I'm just going to make this bigger. If I rewrite this as a power, I have 2x squared plus 3, I'm going to put some brackets in there, raised to the power of 1/2, because that's really what I'm doing to it. Now, we have our function on the inside, so this is my g of x, and then this raised to the power of 1/2 is actually my f at x. So now let's go ahead and let's take the derivative. So we know we want the derivative of the outside. So the derivative of the outside, I'm going to bring my power down. So that is equal to 1/2 times my derivative on the inside, just my function on the inside, times 2x squared plus 3. Now, let's not forget, we have to subtract 1 from our power. That's continuing with the derivative of the outside. So that leaves me with negative 1/2. And now I have to multiply this all by the derivative of the inside. That's what this is telling me here. The derivative of 2x squared plus 3 is 4x. Okay, so now I'm going to rewrite this and put this back together in a little bit more proper notation. So the 1/2 is going to stay out at the front. I'm going to move this back down to the bottom because remember, 2x squared plus 3 raised to the power of negative 1/2. The negative 1/2 just pushes it down to the bottom, and we have the square root of 2x squared plus 3. The 4x will stay on the top. And that is our derivative. So the derivative, I'm going to do one more thing. I haven't simplified it completely. I'm going to get rid of that 1/2. So I'm going to take 1/2 of 4. 1/2 of 4 is 2x, and that is all over the root of 2x squared plus 3. So the derivative of the square root of 2x squared plus 3 using our new rule, our new chain rule, is h prime is equal to 2x over the square root of 2x squared plus 3. So go ahead and add this to your rules to live by so that you have it to use going forward. And we're calling it the chain rule now, not the special case. let's look at an example. So determine dy over dx. Remember, that's our Leibniz notation, dy over dx. It just means the derivative when y is equal to u squared minus u plus 1, and u is equal to 2x plus 1, and x equals 2. So this is a composite function. We need to put this together. So really what this is saying is that everywhere there is a u in our function y, we are going to substitute 2x plus 1. So let's put it together. So y is then equal to, we have 2x plus 1 squared. So I've substituted 2x plus 1 into my u squared, minus u again, 2x plus 1 plus 1. Okay, so now let's take the derivative. So dy over dx, my derivative of y as it relates to x, is equal to. So now we're going to use our chain rule for this one. So I'm going to bring the power down. So it's the derivative of the outside times the inside, and that just becomes 2 minus 1 just becomes 1, times the derivative of the inside. 2x plus 1, the derivative of that is just 2. Now, we're going to take the derivative of this, 2x plus 1. So our sum and product rule tells us I can just subtract the derivative of this. I can just subtract the derivative of that. So the derivative of 2x minus 1 is just 2. And my derivative of 1, well, that's 0. I'm just going to write it there just so we can see it. So we've taken our derivatives. Now let's collect like terms. So I can multiply this 2 and this 2 to give me 4. So that's 4 times 2x plus 1 minus 2. Expand and simplify. We end up with 8x plus 4 minus 2, which leaves us with a derivative, dy over dx, or y as it relates to the derivative of y as it relates to x, of 8x plus 2. So there's our derivative using our new chain rule and a few of our other rules. Now, that's not all that the question is asking, though. The question is asking, well, determine the derivative when x equals 2. So now this is just a case of simple substitution. So if our derivative dy over dx is equal to 8x plus 2, and we want to know what's happening when x is equal to 2, that's just straight substitution. So 16 plus 2, so this will be equal to 18. Now let's look at it in Leibniz notation. So really what this is saying is that because we have two different functions, we have y and we have u as they relate to x. We want to take the derivative of y as it relates to x. Well, we have to turn that u into some x's by substituting everywhere there's a u in our original function to be of some value of x. I hope that makes sense. I don't know how else to explain it. So really what this is telling me here, this dy over du is my derivative of f, of my first function, as it relates to the second function. That gets my x's inside there. And then this just means that it's multiplied by the derivative of my second piece of that function, or the inside. So it's still the derivative of the outside times the derivative of the inside. It's just a different way of writing it. So let's write it out. So we have dy over dx is going to be equal to, we have 2u minus 1 times 2. That's my f prime at g, or f, the derivative of f at x. Now I want to take my dy over dx, and we are going to substitute in I think I should point out 2u minus 1 is just our derivative. So 2u minus 1 is the derivative of u squared minus u plus 1. So that's where that came from. That's just that derivative. And then this 2 is the derivative of my 2x plus 1. So when we're doing it in Leibniz notation, really what we're doing is we're taking the derivative of each one and then multiplying them together. The u kind of just stays there. And we're going to substitute that value in here in a second. So, okay, so u squared minus u plus 1, the derivative of that is 2u minus 1. That's really what this is telling me over here. Then I have my derivative of 2x plus 1. That's just 2. Now we're going to put it all together and substitute in. So now I'm going to substitute in a value, but I need to know what I'm substituting in. So this is where we have to do a little bit of an extra step. So let's do that in red. So I need to know what I'm substituting in for u. We don't have a value for u. I have a value for x, but I don't know what u equals. So I need to figure out what u equals. So if x is equal to 2, what does u equal? Well, u is equal to 2x plus 1. We know that just from up here. So let's substitute in. When x is equal to 2, then u is equal to 4 plus 2, or u is equal to plus 1. Oh my goodness. Okay, math is not mathin' today. There we go. Okay, plus 1. 4 plus 1 does indeed equal 5. So u is equal to 5. So up here where we did a direct substitution of x equals 2, here we're now using u equals 5. Okay, so we have 2 times u, which is 5, minus 1 times another 2. dy over dx is equal to, that's 10 minus 1 times 2. That is equal to 9 times 2. Which is equal to 18, which was what we got before. It's just a different way of tackling it. So when we're using our chain rule, we're going to go ahead and put anything that's u inside of the first function, then substitute our value in. When we're using Leibniz notation, we're going to tackle it a little bit differently. We're going to we're going to take the derivative of both of them and then put it together, remembering that we have to solve for u before we can substitute in because we're not solving for x.